Welcome to chapter 10 from year 2 pure mathematics. This chapter is all about numerical methods, and numerical methods are processes whereby we can solve equations in a non-algebraic way. And today in lesson 1 we're going to look at how to locate roots of functions by considering changes of sign, and this may also be something you'll have covered at GCSE. So I put the word roots in italics. We're going to define a root in the warm-up, and then hopefully we'll have a good primer for what's to come in the rest of the lesson. So please pause the video and have a go at the 4 warm-up questions. Okay, and let's have a look at the results. Okay, so as promised, straight away we've got a definition for the root of a function. So a root of a function, I'll just highlight it again, not defined, it's italicized if that's a word. The root of a function, f, is the value of x such that f of x equals 0. So in other words, it's where the function crosses the x-axis or the x-intercept, or where y is 0. All those are analogous to what a root is. Okay, so roots refer to functions more particularly. Now, the function f of x equals x squared subtract 2 as our first case has a root at x equals alpha. Okay, so the value of the root is called alpha. Okay, that's all we know about it so far. The other thing we know, though, is that it's a positive value. So we're told that it is a positive value. We have to find this value of alpha. Now, the way to do that is to sub alpha into the function. So let's do it. So consider f of alpha. I'll put alpha in green. It's not an A. It looks a bit like an A. It's the Greek letter A. So I'm going to put it like that as a fish symbol, if you like. So f of alpha. Now, if we replace x with alpha, this is going to give us alpha squared subtract 2. Okay. Now then, if we know that alpha is a root, so given alpha is a root of f of x, of f, what that means is f of alpha must equal 0. Okay, so that's just using that rationale. Using the definition of a root, which we were given in the first line, we can now say that f of alpha must equal 0 because the root is the value of x such that f of x equals 0 and x is equal to alpha. So we simply have to solve this equation. All right. Now, we've already subbed in alpha into our f, so we just solve the equation. Alpha squared subtract 2 is equal to 0. Let's rearrange that. So alpha squared is equal to 2. So alpha must equal, I was going to say plus or minus, but it's not. It's just going to be the positive root of 2, since alpha has to be greater than 0. All right, so we can't take the negative value of the square root because that's not how alpha is defined. Although there would be another root when x is negative or alpha is negative, but that we're not considering at the moment. So it wouldn't be called alpha, it might be called something else. Okay, but there would be another root, but we're not considering that right now. Okay, now for part B, it says to evaluate f of 1.41 and f of 1.42. Just to give you some context as to why we're doing that, I'm just going to bring up the calculator. On the calculator, if we have a look at what alpha actually is numerically, so if I choose option 1, take the square root of 2, okay, and set that as a decimal, we can see that alpha lies somewhere between 1.41 and 1.42. Okay, so if we evaluate f of 1.41 and f of 1.42, let's see what happens. All right, so on our screen here. So if we put 1.41 into this, we're going to have 1.41 squared subtract 2. Okay, and we're going to see what that gives us. So we'll go back to the calculator. Let's go to mode 1 again. Menu 1. 1.41, square it, and then subtract 2. What do we get? Okay, and just change that to a decimal. So that's negative 0.0119. Okay, so that's our answer for that. Now, if we put in f of 1.42, so that's going to be 1.42 squared subtract 2. So I can go back and edit this. So just change that to 1.42. And let's see what we get. So we get 0.0164. So what does that tell us? Well, we know those values are pretty close to the root alpha. But what we've actually shown is if we put in a value that is slightly less than alpha, it returns a negative answer. I hope that's clear. You get a negative result there. So that's clearly less than 0. Okay. Now, if we put in a value that is slightly bigger than our alpha, root 2 in other words, we get a value that is positive. So we seem to have a change of sign. Okay, so that's just something to bear in mind. Okay, now let's move on to question 2. All right, so for question 2, we're given an example just to get us started here. It says each diagram below shows an interval AB. And I just want to explain a bit more about what this interval means as it's written. We have the square brackets. Now, the square brackets denote inclusivity. So, in other words, A and B are included in that interval, okay, on the x-axis. So, x is a real number, but the interval is inclusive of A and B. All right, and A is less than B, as you can see from how I've written it. So, the example is draw a continuous curve y equals f of x with 3 roots in the interval. So 3 roots is emboldened to show that that's the important part. 3 roots in that interval. So the interval is clear. It's just where the line occurs. And have we got the 3 roots? Well, yes, we do. The 3 roots are where the curve crosses the x-axis, where f of x equals 0. So we have 1 there, 1 there, and 1 there. So we do have the 3 roots. Okay. So we could call these roots something. We could call this one could be alpha, for example. So f of alpha is 0. That could be alpha. That could be beta. So we know that f of beta would be 0. And sticking to the Greek theme, we could have gamma. So f of gamma would also be 0. So they all meet the conditions of roots. Now, going on to the one we have to do, it says draw a continuous curve y equals f of x with 2 roots in the interval. If you didn't manage to do this, it might be a good point just to pause the video again and have a go at this if it's kind of shed some light from the example what to do. So it can be a diagram with any 2 roots. It doesn't matter. So we just pick 2 points arbitrarily. It doesn't really matter where you pick them. You can do it wherever you want. So I'll pick here and here. That will be good enough. So we'll put some roots on there. So I've just got to draw any continuous curve y equals f of x, and it's got to be continuous. So what does that mean? Well, it means you draw it without taking your pen off the paper. Okay, there is no disjoin along your curve. So it doesn't matter how you do it. It's just got to cross twice. So I'll do something like this. Okay, so that would be a smooth continuous curve with 2 roots in the interval AB. Okay, and you can do any variation on that you like. Okay, if you want another example, perhaps you could start down here and do that. Whatever it is you want to do. Okay, moving on to question 3, we have another continuous function, g. Now this has e to the minus x as the first term, x squared and -2. Okay, now part A says that by calculating g of 1.3155 and g of 1.3164, show that g has a root alpha 1 equal to 1.316, correct to 3 decimal places. All right, well, it says by calculating g of 1.3155. So we'll do that first. So let's see what happens when we do actually calculate this. There must be a clue in doing that. And we also have to calculate g of 1.3164. So even if you're not sure what to do the calculation, then it may shed some light on what to do. So g of, I'll put that in green. So that's going to be 1.3155. Okay, close that bracket. Now we have to replace x with 1.3155 throughout this equation. So this is going to be e to the power negative 1.3155 as shown, plus 1.3155 squared All right, so we'll do that and then subtract the 2. Okay, so we'll do this on our calculators and see what happens. So exponentiate, so shift, that's pi. Oops, I didn't want to do that. Shift E, so put the values in, so it's negative 1.3155. Okay, just make sure the numbers are correct. Just come out of that, plus 1.3155 and then square that. Okay, and then subtract 2. What do we get? Okay, so we get a very, very small number. So it's multiplied by 10 to the negative 3. So if it makes more sense, you could perhaps write that in decimal form, not in standard form. So that would equal, in fact, I better put the equal sign underneath so we've got a bit more space. So it's going to be negative, and it's a very small number. So it's going to be 0.00112. Okay, so that's multiply that. So that's 1.11 times 10 to the minus 3. Okay, so that appears to be right. So that's to 3 significant figures. All right, so we have a very, very small negative number. Now, you may have anticipated what's going to happen next. If we do g of the next number, 1.3164. Okay, now I won't write it all out again when we just plug the numbers in. It's obvious we're substituting it in. And if I just go back to the calculator and just edit these numbers. So we're going to go back to the beginning. So we're keeping the 1.31 bit. We're going to change the last 2 decimal places to 6 and 4. Okay, and then just delete those 2. 6 and 4 again. Just check that's correct. Press equals. All right. So lo and behold, we get a positive number. So we're going to get 0.00101 to 3 significant figures. Okay, so that's interesting. We're getting 2 values, one negative, one positive, both very close to 0. So this suggests something rather important. Because the first one is negative and the second one is positive, we can sort of visualize this, what's going on a diagram. I'm just going to draw this. It's worth looking at. So if I just come down here just to explain what's going on. If we take the x-axis as here, we know that this function g must cross the x-axis at some point. Now, we know that because when you plug in 1.3155 and when you plug in 1.3164, what happens is we get a negative value to a positive value. So when we plug in 1.3155, we're going to get some negative value, but it's going to be close to the x-axis, but on the negative side. And when we plug in the second number, we get a positive value close to the x-axis. So what that means is at some point in between those two values, this curve must cross the x-axis. So that identifies that there must be the root alpha, okay? The root alpha, which is called alpha 1 in this case, must lie between 1.3155 and 1.3164. So we've just verified that. Now, the reason we know alpha 1, as it's called, is 1.316, as is given in the question, which I'll just show you here. We know that that is correct to 3 decimal places because if we round our value to 3 decimal places, we get exactly the same number. Okay, so we know that this rounds to 1.316 because the 5 would bump up the 3rd decimal place to 6, and this one would be 1.316 because the 4 would keep the 3rd decimal place as 6. So we've just shown that this is indeed true. Now for the next bit, it says that the function g has a second root alpha 2 in that interval, so in the negative side, and it says write down the value of alpha 2 correct to 2 decimal places. So we simply have to round each of those numbers to 2 decimal places, which is something you've been able to do for a long time, hopefully. Okay, so if we look at the first value in the interval, minus 0.543, that rounds to, so looking at that 3rd decimal place, okay, that means that nothing is going to happen to the 2nd decimal place, and we can just ignore the rest of the number. That's going to go to 0.54 to 2 dp. And if this is true, then they should both round to the same value. So negative 0.535. Well, looking at that 3rd decimal place there, that's 5 and above. The rule states that if that's 5 and above, the 2nd decimal place has to tick over to the next number. So this is going to be negative 0.54 to 2 decimal places. So indeed, we have just verified it, which is great. Okay. So alpha 2 is just going to be 0.5, negative 0.54. Okay, so I hope that makes sense. Now, moving on to question 4, we have some curve sketching to do. Now, question 4, bit of revision on curve sketching, although these are standard functions that we should know. So for the first curve, we have 1 over x squared. So I'll just do that in blue. And again, you just have to look this up if you're not sure how this looks. So it's asymptotic on the x-axis and the y-axis, and purely positive because we're talking about square numbers here. And then if we look at y equals the natural log of x, so I'll do that. I'll just label it, in fact. So blue curve is y is equal to 1 over x squared. And if I now add y equals log x, another standard function, we know it's going to go up like this. So this is going to be y is equal to the natural log of x. And we have an x-intercept at 1. And again, it's asymptotic on the y-axis and purely positive x values only. So it says, use your sketch to determine the number of roots of this equation. Well, if we're interested in the number of roots of that equation, what you'll notice is if we rearrange the equation slightly. So if we write it as log x is equal to 1 over x squared, that would be as simple as determining where my two graphs intersect. Where is the natural log of x and 1 over x squared the same? Well, it's clear. It's right here on the diagram. We don't have to solve it. We just have to determine the number of roots. So clearly, if there's one point of intersection only, and there will only ever be one point of intersection, we've just shown it without doing anything technical whatsoever. So there is going to be one root only. And this is the type of equation where you would have to use numerical methods in order to solve it. Okay, so let's have a look at how to locate roots of functions. So we have a bit of an introduction to the main idea. And we know what a root is. We've defined it as a point of intersection with the x-axis. So in other words, if you have a function f, it's when f of x is equal to 0, and that particular value of x that leads to f of x equaling 0, that is your root, essentially, which we sometimes call alpha, or other denominations very similar. So what we've done is, because we've defined what a root is, we can have a look at what actually happens in a particular interval of a function. Okay, now if we have a look at this main idea, we have three cases presented to us. So, and we have three different functions. We have f, g, and h, and we have the same interval. Okay, a, b, and I'll just remind you of what a, b actually means with the square brackets. It means that a and b are an interval with a and b inclusive, and a is going to be less than b. So that means that there is something between them. Okay, they're not necessarily equal to each other. Okay, but there is something between them. Now, if in case one, we're going to make a few sort of pick out a few key properties of what's happening in each version. So I'll just scroll down a little bit while we talk through this. So for the case one, I'm just going to clear that as well. So for case one, what can we deduce? Well, let's first of all look at the number of roots that we can see. Okay, and this is for f of x. So we have a single root there, so we're going to write that down. So f has one root. What else can we deduce? Well, it'd be interesting to look at how f is behaving at the extreme ends of the interval. So let's have a look at a, this point here, and b over here. So what can we determine about f in this case? Well, we can see that f of a is negative, and we can also see that f of b is positive, assuming that line is the x-axis, of course, which it is. And there's nothing much else to say about that. We know we've got one root, we've got a change in sign at a and b. So let's move on to case two. Let's have a look at similar analysis. Well, how many roots do we have at case two? And by the way, if you want to pause the video, try this yourself and then come back and we'll go over the results together. I would strongly recommend you do that. So for case two, we have 1, 2, 3 roots. So that's good. So let's just write that in. So g, this function, has 3 roots. Okay. And I probably should stress actually that this is on the interval AB. We can't say anything else about the rest of the real number lines, but we can say it about AB. So I'm just going to add that. Okay. And what's happening at the extreme ends? Well, we can see that G of A, I apologize. G of A, once again, is negative. And G of B is definitely positive. Okay. Now, there's also something else to bear in mind here. You've got things like maxima and minima to consider. We're not going to look at that in this instance, but that will play a part when we're looking at the changes of signs and things like that. Okay, so let's move on to case 3 and deduce the number of roots that we have. So we seem to have 1, 2, 3, 4, 5 this time. Okay, so we seem to be going up in 2s. So let's just make a note of that. So the function h has 5 roots on AB. Okay, and what's happening at the extreme ends? Well, we can see that h of A this time is positive. Okay, fair enough. And h of B is negative. So let's just have a look at what's going on. We've got the number of roots. Now, what's the key property? What property do these number of roots all share? If we look across, we have 1 root, 3, and 5. Okay, in these 3 cases. So it appears we have an odd number of roots, first of all. So 1, 3, and 5. And we also have, looking at the extreme ends, we have changes of sign. Okay, so we've got negative and then positive, negative, positive, and then positive, negative. But whatever happens, there is a change of sign. So how can we sort of build a theorem around this? Well, let's have a look at that in the next step. So what can we deduce from all this? Well, we know that if we have a function f and it's continuous on an interval, so we're going to state that. So if f is, I know there was f, g, and h, but we'll just, for generality's sake, we'll just call it f. If f is a continuous function on some interval of the real line, so on the interval AB, we needn't specify anymore. We know we're talking about an interval of the real line with A and B included. So if f is a continuous function on that interval, and we need another condition, we've got space for something else, and f of A and f of B are opposite signs. So we notice that we could have f of A is positive and f of B is negative, but there's nothing stopping us having it the other way around, where f of A is negative and f of B is positive, as long as they are opposite signs. And you can stress that a bit further if you want to. If you want to show what that means mathematically using symbols, that's fine. But that will do. So if we have those 2 conditions, if f is a continuous function on AB and there is a change of sign between f of A and f of B, and note that A and B are the extreme ends of the interval. So f of A is, of course, the first point in the interval, and B is, of course, the second point in the interval. So if that's the case, what happens? Well, we have deduced that there is at least 1 root there is at least 1 root in the interval AB. Okay, and we can also make a stronger assertion. Not only is there just at least 1 root, the number of roots is odd. So we're making a bold claim here. We're stating that there is at least 1 root, but the number of roots that you will have, if it's not 1 itself, would be an odd number. So let's see if we can test this idea in the next three cases. So we're going to have a look at cases 4, 5, and 6 and just verify that this theorem does in fact work. So for case 4, we've got no description given here, but we do have a diagram. And what we're going to do for cases 5 and 6 is we're going to construct the diagram, the graph, the continuous graph, if it is continuous, of course, using the description we've got. So for case 4, let's have a look what we have here. We've got y is equal to u of x. Now the function is, the curve is drawn for us. Now we can see that there are two roots in this interval. So let's just have a look at some of the properties. So we have two roots in the interval AB. Okay, you can see that clearly. Now that breaks the theorem in essence, because we've got two roots in AB. But let's just have a look a bit further, because if we've got two, that violates the implication, doesn't it? Okay, so we've not met the implication. But let's have a look at the initial conditions. Is U continuous, first of all? It has to be continuous on AB. Well, we can say that. So we can say that U is continuous on AB. So that meets the first condition. So that's the if condition. So we've met that. Do we meet the second condition? Is there a change of sign between U of A and U of B? Well, let's have a look and write it down. So we can see that U of A is negative and U of B is also negative. So that means that that first condition is not met. Okay, so that means that the theorem has not been violated, because to set up the theorem, you have to meet the first two conditions. The first condition being that U has to be continuous on AB. That's been met. But the second condition has not been met. So it doesn't matter that it has two roots, because we haven't met the conditions for the theorem anyway. Okay, the first two conditions have not been met. So we'll just make a note of that. So condition 2 was not met. Remember that condition 2 is that the function has to have a change of sign at A and B. Okay. Now let's have a look at case 5. We're going to have to draw this. So we're told that V is continuous on AB. Okay. So it meets the first condition. That's good. Now it doesn't meet the second condition, because V of A is positive and V of B is also positive. So that's not met. Now, if that's the case, then the overall theorem is not valid. Okay, and we can see that because V of X is not equal to 0 on AB. So that means that there's no root to speak of. So we'll just make a note of that. So that means that there is no root. Okay. And again, condition 2 is not met. Okay, hope this is making sense. Now we'll have to try and draw this. So we know that V of A is positive. I'm going to have a go at drawing it. V of A must be positive, so I'll put it somewhere up here. That's V of A. Okay, now V of B is also positive, so I'll put that there. So as long as it's positive, it doesn't matter how you've done it. And it's not allowed, there's not allowed to be any root on that interval. So all we have to do is join v of a and v of b together without crossing the x-axis. So something like this would be absolutely fine. So that would be case 5. So we've got no roots in this case. Now for case 6, we have got the first condition is not met. Okay, it says W is not continuous on AB. First condition not met. Right, so that means I'll just make a note of that. So condition 1 is not met. It's only if the first two conditions are met that the theorem is valid, okay? So it's not continuous on AB. We'll have a look at what that means in a moment. We also have, the change of sign though. So we do have the change of sign. Okay, so that second condition is met. But the theorem states that if the second condition is met, then and the first condition, then we should get an odd number of roots. But because that first condition is not met, we shouldn't get at least one root, and the roots shouldn't be odd numbers, of course. And we can see here that we've got no roots whatsoever. So how can we show this discontinuity? Well, it's actually quite easy. If I show that W of A is greater than 0, so I'll put W of A somewhere up here, like that. And W of B is less than 0. So W of B will be somewhere down there. But if they're discontinuous, so if there is a discontinuity on AB, all I have to show is that if I draw it, let's say that W of A is doing this, and then there's a discontinuity, and then it starts again here perhaps, and does that. Okay, now that is a discontinuous function because I had to take my pen off the page when drawing it. Okay, so all of this, cases 4, 5, and 6, prove that the theorem does indeed work, and they are sort of counter cases, counter examples, whereby the one of the two conditions are not met, and therefore you get a bogus number of roots if no roots at all. So if we just have another look at this, in the first one, we got an even number of roots, which is not supposed to happen, but that's because condition 2 was not met. And in cases 5 and 6, there were no roots at all. And again, one of the conditions were violated. So you can obviously do variations of this, but hopefully that makes some kind of sense. All right, so let's have a look at a worked example on locating roots. And it's quite similar to the kind of thing you might be asked in an exam situation. So we have a function f, and we know f is continuous on the given interval 1, 2. So that's including 1 and including 2, as stipulated here. And it's a cubic, and we have this character Oswald. Using his calculator, he observes that f of 1.1 is negative, and f of 1.6 is also negative. So given that evidence, he declares that f of x has no roots in the interval 1.1 up to 1.6, not including either of them. If you just to recap, if it's curved brackets and not square brackets, what that means is that the interval we're talking about does not include 1.1 or 1.6. So I better just stress that before we start. All right, now what we could do to do the diagram, we've got space for a diagram here, but I might use that later on probably for part B. So for part A, we'll just do a small diagram, and it's quite similar to the idea we were talking about a few moments ago. So let's draw an x-axis, or an interval on the x-axis. So let's draw that, and we'll call the interval 1.1 up to 1.6. So we've got 1.1 here, 1.6 here. Neither of them included. If you want to, you could put the the hollowed out circle at either side, just to show that they're not included. Now, according to Oswald's work, he states that f of 1.1 is negative. We'll assume that's true. So that would put the point f of 1.1 somewhere down here. I don't know where it is exactly. Okay, but that would be f of 1.1. We just know it's negative. And also f of 1.6 is also negative. So we'll put that just a slightly different value, maybe somewhere there. Doesn't matter where you put it. Okay, so we don't have a change of sign. They're both negative. Now, how can we show that he might be incorrect? Well, if you look at one of the cases 4, 5, or 6, it's not necessarily the case that two signs being the same shows that there are no roots in the interval. Okay, to break the theorem, we've not met the second condition once again. We don't have a change of sign in the function. But if the theorem was true, if the conditions are met, then that would show you that you have at least one root in the interval, or an odd number of roots. Now, in this situation, to break that theorem, you would either have no roots at all, or you would have an even number of roots. And we can show pretty clearly from this just by drawing a nice smooth curve, like something like that, that there are indeed an even number of roots. Okay, now you could have two. I could have done that multiple times and got 4 roots, 6 roots. It doesn't matter, but we can very clearly and easily show that we create 2 roots there and there. All right, so that would be a suitable diagram just to show that just claiming that there are no roots in that interval is false. Okay, it might be true, we don't know, but it could be false. So he cannot declare that with the evidence he's got. Now for part B, we're told by calculating 3 values of f, explain why f has at least 3 roots in the given interval. Okay, so let's just scroll down a little bit just so we've got a bit more space. So I'm just going to move that down there. And I'll just need f on the screen as well. Okay, and we'll just erase some of this. Okay. Now then, in fact, I can get rid of this diagram as well. All right, now for the diagram here, we first need to calculate f of those particular values. And just bear in mind, we'll just keep a summary of information. We know that f of 1.1 is negative, and we also know that f of 1.6 is negative. They were given to us. So we'll just keep those in the bank as well. So just put B here. So we know that f of 1.1 is negative. You'll see why I'm going to use this in a moment. So we need to calculate the next number. So that'll be f of 1.3. So we're going to sub in 1.3 into our function. So we're going to get our calculators out for this. I'm going to find out what we get. So on our calculator, so we'll put the function in, and what we'll do, we'll put the function in once, and then we can just edit the numbers as it for the inputs. So if we do 54 multiplied by 1.3 raised to the power 3, it's cubed. Subtract 225 multiplied by 1.3. This time it's squared. Okay, and then we're going to add 309 multiplied by 1.3, and then subtract 140. And what does that give us? Well, it gives us 11 over 125. Let's have that as a decimal. So that's 0.088. Okay, great. So that's 0.0. Just get rid of that. I'm not on the right function here. 0.088. And what we're interested in is the sign. Now it's clearly positive. Okay, it's small, but it's positive. Okay, good. Now we can put in the next number. Now the next number we're interested in is 1.5. So we've done 1.3. We'll do 1.5 next, and then we've got to do 1.7. Okay, so let's do that. So f of 1.5 now. And again, you just edit the calculator. You don't have to type it all out again. So going over to the calculator, let's come out of that. Just go back to the start first of all. So wherever I see a 1.3, I'm just going to change that to 1.5. So delete that, change the 3 to a 5. Delete that, change the 3 to a 5. Okay, and I think that's it. Okay, so we get negative 1/2. So that's minus 0.5. Just keep it in decimal form, which is negative. Okay, so we have a change of sign between 1.3 and 1.5 for our function f. The next one, now we know 1.6, that's also, we know that's negative also. So we're going to make a note of that as well. So f of 1.6, which is given to us, is also negative apparently. So I don't know what it is. I'm not going to work it out. We just know that it's negative. Okay, and that was given to us earlier in the question. So just here. Okay, that might be useful. And the last one we need to work out is f of 1.7. So f of 1.7. Let's put that in. So close the bracket and see what this equals first of all. So again, we'll just go back to the calculator and just edit our inputs here. So change that to a 7. Change that to a 7 as well. And change the first one to a 7. So let's see what we get. 44,125, so that's 0.352. Okay, so we've got our values. And we know it's positive. Remember, the sign is important. Continuity of the function, which we've got, we know that, and the sign is really important. Now, how do we apply this? Well, we're going to show this on a diagram. It says, by calculating all these values, explain why f has at least 3 roots in the interval. Well, I'll show you on a diagram what's going on here, first of all. So if we draw the interval, I know you're not asked to do this, but it's worth doing anyway. I'm just going to show you what's going on. The interval we're working on is between 1.1 and 1.6, sorry, 1.7. So we'll just indicate those on here. So we'll start with 1.1. Okay. The next value we get is 1.3, which I'll put about there. Then we have 1.5. Then 1.6. And then 1.7. Like that. So that's the interval. Now let's just consider what the function is doing at those points. So at f of 1.1 we know is negative. We don't know what it is. I'll just put it somewhere here. We know it's negative. F of 1.3, I'm just looking over here. That is positive and it's small, so I'll put that somewhere around here. F of 1.5 is minus 0.5, so that's quite negative. I'll put that down there like that. F of 1.6, we don't know much about it other than it's negative, so I'll put it somewhere here. And then F of 1.7 is positive. And again, we don't know how positive. So according to the theorem, we know F is continuous across this whole interval. So the first condition is met. The second condition is also met in this first instance. So if we just look, first of all, at the interval between 1.1 and 1.3, we have the change of sign. So that means that there must be at least one root between 1.1 and 1.3. It could be more than one, but we know that there's at least one. So for the roots here, more than one, okay? For that first bit. Now for the second bit, again, we have a change of sign. So we'll look at the second part of this interval. So 1.1 to 1. Sorry, I beg your pardon, 1.3 to 1.5. What's going on here? Well, we have the change of sign. Again, the theorem states that we've got at least one root. Okay, in that interval. So just calling them off so we know what we're talking about. So greater than 1, or I should say greater than or equal to 1. My apologies. Greater than or equal to 1 in the second bit. Okay, so those two sub-intervals or partitions of the main interval, they both meet the theorem requirements. They both have continuity and they both change sign at the extreme values. So let's have a look at 1.5 to 1.6 next. So this next part, going from there to there, we don't have the change of sign. Now, that doesn't necessarily mean that there is no roots, okay? But it does mean that there is either no roots at all or an even number of roots. So for the sake of this, because we're looking at the least possible we can have, then we'll keep it as no roots. So the least possible is 0 for that interval. Okay. And for the final interval, well, we have the theorem is met. So we have the change of sign. So we can say that there is at least one root. Again, there could be more. Okay. So for the last one, greater than or equal to 1. Okay. So we have the 4 subsections, and I didn't highlight the last one. Why not do that just for completeness? There we go. So for the 4 subsections, we have greater than or equal to 1, greater than or equal to 1, greater than or equal to 0, greater than or equal to 1. So we need to add up all these. So the total would be 1 plus 1 plus 0 plus 1, which equals 3. So there are at least, because it's greater than or equal to, remember, 3 roots in the interval. (1.1) not inclusive up to 1.7 not inclusive. Okay. Now then, if you want to not use a diagram for that, you would just argue the same thing. You would just say, okay, f of 1.1 is negative, f of 1.3 is positive. So going back to what we've got here, okay, that bit greater than or equal to 1. Then you would look at f of 1.3 and 1.5, those two. Again, the theorem is met. There is a change of sign. So that would be greater than or equal to 1. And then the next two, so you need to see how it's staggered. Theorem doesn't work, but we know that there would be at least 0. And then the rest of the number of roots would be even. And then the last part, the theorem is met. We have a change of sign. So we'd have greater than or equal to 1. And again, just adding up those numbers, 1, 1, and 1, and the 0, you get at least 3 as your total. All right, so that's for part B. Now for part C, we're going to have to show that alpha is equal to 1.67 is correct to 2 decimal places. Now we can do this very quickly, just on the screen without kind of erasing any of this. So alpha is the root. So we can state, because it's given to us in the interval, that alpha is an element of that interval 1.6 up to 1.7, if you just remember your notation. So alpha is contained in the interval, which is a set of numbers 1.6 up to 1.7, and they're real numbers. Now, to show that alpha is indeed 1.67 correct to 2 decimal places, we can use bounds. Okay, you may have done this for GCSE. So we can use the upper bound and the lower bound. So I'll just do this over on the right-hand side, up here. So this is for part C. You can do this at the bottom of your page. You'll have plenty of room. So we just first need to consider what the upper bounds and lower bounds have. So you probably got your own techniques for doing this. Firstly, I just add an extra decimal place. So we can say alpha would equal 1.67, and then I'm just going to put an extra placeholder on the end. All right, and then what I tend to do is just consider the last 2 digits. So it looks like a 70. Okay, and then for that 70, I know it's not 70, I'm cheating a bit. If you add 5 and subtract 5 from 70, that will give you your upper and lower bound, respectively. So if we do the upper bound first, I'll just make a note of that. So you just plus or minus the 5, just purely from the last 2 decimal places. Remember, I've added a 0 as a 3rd decimal placeholder. So the alpha upper bound would be 1.6, and then I add 5 to the 70, essentially. So that would be 75. Okay, and then the alpha lower bound, the alpha lower bound would be 1.6, and then I have to subtract 5 from the 70, so that would be 65. So that's 1.665. Just a technique that I use. Okay, you don't have to do it like that. Great. Now we have to show that we have a root at alpha equals 1.67 correct to 2 decimal places. So what we need to do now is calculate f of each of those. So therefore f of 1.675 and f of 1.665. So let's see what they are now. So we'll get our calculators ready. Let's drag this over. Okay, so I've just cleared some of that away. Now we're just going to plug in those numbers that we've just written down. So the upper bound and the lower bound. So we'll do the upper bound first, which is here. So we're going to plug that into our f function. So let's do that. So it's going to be 54 multiplied by 1.675. That's going to be cubed. Okay. Subtract 225 multiplied by 1.675 squared. All right. Add 309 multiplied by 1.675, and then we just have to subtract 140 from that. And let's see what we get. So we get a small but positive number. So you'll be thinking, what we're hoping to get for the lower bound? Well, we're hoping to get a small but negative number just to verify. So that's 0.0782 roughly, or 81 ... which is positive. So if the root exists, there should be a change of sign here. So let's check. So we'll go back to our calculator and we're just going to edit what we've just inputted. So change the 1.675 to 1.665. So do that, change that there. Go back to the next one. It's going to let me. There it is. 65 there. Okay, and go back to the first one. Get rid of that. Change that to 65 and press equals. And there we have it. So we have a negative value. We've just verified that there is a change of sign. So this is negative 0.0148, and I'll just put dot, dot, dot. This is negative. And we can use the theorem now, okay? So we know that there's a root because just explaining why. F is continuous, we know that. So from this, there is a change of sign. So therefore, alpha, let's get rid of that, equals 1.67 is correct to 2 decimal places. And I apologize for running out of room there, trying to squeeze it in. So what you're trying to do is you're showing the change of sign by subbing in the upper and lower bound. Both of those values, of course, will round to 1.667. Now, I know we're taking a bit of license with this because the upper bound doesn't technically, but the way to do it is to take the upper bound as 1.675 and the lower bound is 1.665. You're adding a bit on and taking a bit off, and if there's a change of sign, then there must be some point between where it crosses the axis. Okay, so I hope that makes some kind of sense. There is an exercise to follow which will give you some practice at locating roots.